Oh, oh, oh. Hey, thank you. Thank you very much for catching that. Okay. So, yeah, I'm doing Advent of Code. Day 22 is coming up soon. 12 minutes, in fact. And I was just going over my day 21 solution, which, as I was saying, was a lot simpler. Well, it's very simple. There's only one part where we're doing any sort of algorithm, right? Here's a BFS search starting from a given point, and then we just sum up a bunch of these values, right? Hi there, Isabella. Isabel B. Um, but my issue yesterday, I have even coverings and odd coverings. These even coverings and odd coverings, they represent these tiles, right, of the grid. Um, this dotted line represents the boundary of research, how far we can possibly walk. And some of these are even, some of them are odd, which is to say a different subset of their corners are selected, right? So if this one has the corners all selected, then this one will not have the corners selected, but they'll both be checkerboarded just in different ways. And my issue yesterday was that I thought there'd be about as many evens as there would be odds. But as you can see here, going along this diagonal, they all end in an even, right? So there are going to be more evens than odds. And specifically, if you look here, I have evens marked in red, odds in green. There's going to be like 4 by 4 of the evens, and they're going to be 3 by 3 of the odds in this small example case because they form this like checkerboarding pattern. So it's not going to be half. And what I had yesterday was like half plus 1-ish. I thought that, yeah, I've been over that. So that's what this is here. Full grids. Full grids is this number 3. It's the number of full grids you have away from the center. And that will be the area of the green one, so the odd one. So that's full grids times full grids, number of odd coverings, and then full grids plus 1 for the even coverings. And odd coverings, we just count an odd number of steps enough to cover our example data. And for even coverings, we cover the example data, but just with an even number of steps. And I do something similar for all of the little corner edge pieces here that don't have a full, that aren't a full grid selection, right? So here, there's one where you're searching from the midpoint, and here's one where you're searching from a corner point. In fact, there are 2 different examples where we're searching from the corner point. Oh. And I can show them here. Right here, you're 64 steps in, here you're 195 steps in. And here you're searching 130 steps in from the midpoint. And those numbers, which I'd hard-coded yesterday, now I just compute them from steps remaining, which is this modulo, this remainder, after you take out all of the big grids, right? So steps remaining, this 66 value is if you were to walk all the way to this top right corner point here from the center, how many steps are left? And you have 66. So once you walk to the bottom left corner of this one, you have 64 remaining, etc. So I just do those calculations. And then now up here, I defined all these points, right? The corner points and all the midpoints. And I take those points and I search from them the appropriate number of steps. And then I do my appropriate multiplications down here. So small corners for each of the corners, there's full grids plus 1. And you can kind of see that here. Like here, there's 2 full grids out. So the small corners, one, or the big corners, the ones on the inside, there's exactly full grids, number of them. And there's 1 extra small grid right here. And then these far corners, those are these pointy bits here at the very edge. And that is just, well, one of, there's just 4 of them. 1 for each of the midpoints. And that's my solution. Nothing advanced at all. In fact, I developed like basically the solution within the first hour. I almost leaderboarded last night. And then I kept going over the math all night. And it never occurred to me to check this assumption about the number of even and odd coverings. I mean, it did occur to me to check it, but the right solution never occurred to me until I went to bed and couldn't sleep because the problem was still ringing in my head. Um, but I got there. Now my solution is like 50 lines of code, most of which is just variable assignment. Um, and I'm pretty happy with it. So I was just going over that. We have 10 minutes until the next problem comes out. I'm just going to set up my workspace a little bit. And I think I probably want to close out this worksheet because it does take some time to compute, like 10 seconds, and I don't really want to be spending my CPU on that. So let's say this is day 22. Oh, let's go to the metals tab so we can see what's happening with our worksheet. Oh, it says it was 21. It says it takes 5 seconds, maybe 10 seconds to compute it. I don't know why it takes that long. I'm not really doing that many searches. But oh well. There's perhaps a faster way to compute this, which is by just taking the number of even or odd tiles within a grid. You could take those, and that's just multiplication to calculate that, and then you count the number of grid points that are either odd or even. That's honestly probably faster because you subtract that. You subtract that number of rocks. Let's switch this to day 22. And we have a worksheet ready. In my 5 minutes, do I dare doing some refactors to my AOC library? I think that before I do that, I should do some mits so that I can very quickly stash what I have here. This we can shift an area over, and that could come in handy. Rather than like shifting all the points it's contained in. What's this change here? Is this even a change? Oh yes, I made it return integral, any number for its size because int has a danger of overflowing often with these problems. And I wanted to perform this refactor for the rest of the area, make it take an integral range in general. And that's for stuff I want to implement, which we can save for later. And some to-dos. Okay. I won't really have time to work on this. I'm just going to close it for now. That can be for a day when we have more time to warm up. We'll leave this ready. And I'm just going to do a check on the leaderboards. We have 2 minutes left. Okay, my alarm's about to go off. 2 minutes. I thought I had 5 minutes. Time flies. Okay, my ranks. I felt so close to getting actually top 100 on part 2 yesterday. Because I had my general solution down on paper or down on code. in like the first 40 minutes or something. I just couldn't debug it. Oh well, oh well. That's I think the closest I've gotten. Um, I mean, rank wise, I've been like down in 300 a few times last year. We don't need this. So this is my personal leaderboard, which um, you know, exclamation point AOC, bang AOC to join that. I'm fifth on it right now. These two are way beyond everyone else. They've been neck and neck, and 300 points past third place. So there's no challenging that. You can kind of see. You can see here. This tells you the percentage of potential points they have. This person's at 98, 99% of available points, and then everyone else is at like 84%. I want to sort by total points for yesterday. Yeah, 88 and 86. They're both going to be 86 or above every single day. Wait, is this sorted by total points? There we go. But more interesting to me is a Scala Center leaderboard. I mean, I don't say it because I'm on top right now, but because it's been a struggle for me. I've been trying to stay ahead of Jan Peter over here. I've had a few days where I've taken like big chunks lost, and just yesterday I finally got back up, and I want to maintain that lead. And there's a few interesting dark horses here that had a late start. How did I do this? So here's myself, and here's Jan racing to the bottom. And then who's come from behind? So Raymond, late start, is number 3 or 4 on the leaderboard right now. Oh, with some potential. You can see a potential here to finish if they finish day 21. And then Javadoc. And then the fastest person on this leaderboard is Merlinorg, who you can see their climb here. They had a late start, they missed some days, but on this podium, look at all those gold medals. Some of them are like double gold. A bunch of them are double gold. That's a person who, if they're around, they want to be the first, they can just take the first. Okay, that's my alarm did not go off. Oh no. I've been talking too long. Here we go, day 22. Okay, enough sand has fallen. I can finally filter water for Snow Island. Well, almost. Blah, blah, blah. Here's the input. Okay, so yes, that's 3D. Is this a 3D map? These are coordinates. Represents the position of a single brick at the time the snapshot was taken. The position is given as 2 coordinates, one for each end of the brick, separated by a tilde. Okay, we have 3D points. Some bricks will need to be disintegrated. Cool. 222 means both ends of the brick are the same coordinate. That brick is a single cube. Lines like this represent bricks that are 2 cubes in volume, both oriented horizontally. So this is 10 to 10, and then 1. So this is a 3D area. These coordinates represent a 3D area. I have all this down for a 2D area. and I'll just need to adapt to that code for 3D area. Okay, bricks are stabilized, they never rotate into weird or situations. Okay, what's the question? How many bricks could be safely chosen as a one to get disintegrated? Brick A cannot be disintegrated safely. If it were disintegrated, bricks B and C would fall. So look at the ones that are supporting each other. So we basically sort by the Z coordinate. Um, let's see. Brick A is only bricks. Okay, so we make a graph of what's supporting what, and we look for graphs. Yeah, we need an adjacency graph, and we just look for leaf nodes on that graph. So I guess we would search the area above A. I wonder if I could just keep using my normal areas. Okay, I'm going to represent these as a single area plus a range. Are they always going to have the same XY area? And which is Z? Which one is Z? So we'll just call this our input. Val coordinates equals input dot map case. And what is it? X1 comma Y1 almost Z1 followed by tilde. And I wonder if Copilot can guess the rest here. Probably not. Okay, X2, Y2, and then Z2. Yeah, so I don't have to modify my code. It sounds like I won't have to. I'm just gonna do an area and a range. Are all of these bricks like 1, 0, 1, 2, 1? Y goes from 0 to 2. X goes from 1 to 1. Okay. Okay, so we have val area equals area. Almost not quite what I'm looking for. So x1 to x2 to int. I really want to represent these as intervals. And then y1 to y2 to int. And then val depth equals interval. I might need to normalize this. Let's check that all of these okay, val y range and assert x range non-empty and y range non-empty. And you know what? Z range non-empty. Oh, sure. Interval that from from here dot from oh, I guess dot apply to a range. Yeah. Oh, yes, this is arranged in here. Z range. I'm taking too long doing this. Z range not empty. Z range right here. And then what we'll return is area to depth. Okay, and all those assertions pass. And then we are going to sort these coordinates dot sort by Z range. Dot min. In fact, I'm gonna give myself a case. Area. I guess we're calling it depth. Depth dot min. And then what do we do once we sort it? Well, I suppose we check any of the future coordinates. You don't want to make this n squared. Oh, I know this. I think actually we might want a scan. So we start by sorting them. Well, I think we can just do a scan left. Yeah, it's been a while since I've worked with interval problems like this. You know what? Let me draw this out. Okay. So we have a bunch of things. Let's say these are the z ranges, right? There could be, well, there actually can't be gaps. It might look something like that, except not really, because these have to be, these bricks are like laying on top of each other. Let me look at the problem again. So like the bottom one is laying the floor. The ground is at z equals 0, and it's perfectly flat. Okay, so we could index them by their bottom. And once we find a brick, we look at its top, and then we look to see what bricks are on top of that. Yeah. And how many bricks could be safely chosen? A cannot be disintegrated. B and C would fall because B is one of 2 bricks. um, and I guess they could be stacked as precariously as we want, as long as there's no open gap. What if 2 different bricks are supporting the same brick? B is only one of, okay. And C is the other brick. So we would count both of those. We can't disintegrate them both. I guess we can zip with index and return the indices of these. Coordinates that, yeah, I'm just gonna put this sort by on the coordinates here. Excuse me. And then coordinates, I'm gonna zip with index. dot map dot swap, and then two maps. I guess we have I can just put that at the end of all of this. So now this is a map from their index so that we can reference them. Um, and make a tree. Uh, we do this with like, no? Okay, we'll do this. Coordinates dot map case index, and then to the right is going to be the area and the depth. And for each of these, we can just find yeah, we'll do like the coordinates and depth dot max plus one. Am I going to do plus one? If A is supporting B and C, it is going to be max plus one, right? Yeah. Depth dot max plus one. Oh, okay. So this is my adjacency. Well, edge. We just take index to. Well, I guess we want all of those. When we did this zip with index. Oh, hold on. That's sort of right. I think I want them mapped by their min. Yeah, so we're not gonna do this here. Well, by min. So this could be a map dot has to be. Hi there, children. Dot map case area depth to depth dot min. And then that to, I suppose, the area, or the area and the depth. Um, or the index. The index. Okay, we do want zip for the index. Okay, so now we have an index, area, and a depth. And we want depth.min to the index. This is dangerous. What we're actually going to do to list.map. And then we're going to do a group map, a group group by that first one. And this should be a map of int to a list of int. The given a depth, get a list of indices. found a list of int. Oh, so we want this to be a group map. Okay. Great. Now for the adjacency graph, we can take our index. That index is going to go to bymin depth.max plus 1. Yeah, and then we need a filter on this. So after this part, we have an index going to a list of int. And we want chords. I'll also call them I and j. So we want coordinates j dot area intersects our area. Do I have an overlaps function defined? Point overlaps. Okay, we're just gonna do intersection and area that intersect coordinates I area. Yeah. Oh, hold on. We'll call this candidates. Filter is going to happen on this list of ints. Well, overlapping. So we're going to do this bymin dot filter. And it's going to look something like this here. Or actually, this is going to be a bunch of candidates. So bymin candidates. We'll say I. So each of those I coordinates I dot 2. Wait, coordinates I should give us an area. Yeah. So I guess it is dot underscore 1 dot intersect with our area is not empty. Okay, this overlapping is now our list of ints, and now we have our adjacency graph. So index to overlapping. Okay, and now we take index dot values dot Latin distinct, and then we're gonna let's just to set and then diff against the keys. Diff index dot keys, and then I guess this is a count. That size of that. That size. And this is metals. Extension. Wait, this is edge. Edge dot values. Edge dot keys dot key set. Key set. We have an issue here. Oh, yes. We can dot get that in case it doesn't exist. And we could flat map. Or like we can fold, I guess, on that. We can get our else. Get our else empty list. That works. I know there's nice ways to do this, but we just want this to work. Um, okay, and I'm getting a 0 here. Not quite what I want. Let's look at our adjacency graph. Um, fine. And too many of these are empty, not supporting anything, apparently. Um, I wonder if our buy min is all right. Hmm. So we get a bunch of potential indices by checking buy min, and then we further filter them. Hmm. By checking that they actually intersect with the area of this one. And then we say index overlaps with that. This could also be a coordinates.count. Count the number that don't overlap with anything. But I guess I want a full adjacency graph. Okay, no point in staring at this. What I'm going to do is put in the example and take a closer look at what goes wrong here. Here's our example. Not doing sorting anymore, or we don't really need to sort because we create this by min. It's probably fine. Okay, so our coordinates. Let's do a print line here. Coordinates for each print line. Oh, we haven't actually changed our input. Let me do example. Hey, I suppose we might as well sort that. Okay, so these are the heights of them. I guess that's translate A to whatever. Yeah, let's do a translation. Coordinates dot map. Oh, no, there's a sort by underscore one, and I'll just copy them for each print line. Okay, so there's A, what we're calling A. And let's make sure I have these in the right order. So A is this wide, and then that's the depth. It goes 1 to 1. Okay. A is supporting B, right? 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6. Oh, these depths are all wrong. I need to get myself a way to construct these without worrying about the order. Let's just do this. X1 dot min x2 min these values to int and here we're gonna take the max of those two. Oh wait, we have to int them first. Okay. Okay. Not like ideal. Wait, to int. Hey, good morning, good morning. Welcome back. We have a syntax issue here, right here. I just need to delete that. Oh, no. Okay. Now let's see if these appear properly. The Z range is still weird. Are these all really one high? I don't believe that. Um, maybe X, Y, and Z aren't in the order I think it is. So yeah, two X, Y, Z coordinates. Great. This is 1 to 1. This is 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6, and then 8 to 9 on the last one. 8 to 9. Oh, I guess that is correct. But their example says A is supporting one of these, like supports two different bricks. A supports B and C. How can A be supporting B and C if it's not even close to right? If it goes 1 to 1, B is 2 to 2, and C is 3 to 3. I'm misparsing these. A line like 2, 2, 2 means that both ends of the bricks are the same coordinates. Brick is a single cube, yeah. So 10, 10. These are two cubes in volume, both oriented horizontally. Second brick goes in the y direction. Yeah. Wait. So this extends in the x direction, 0, 1. Yeah. Second brick extends in the y direction, 0 to 1. Okay. Some bricks will still be in the air. You need to start by figuring out where they will end up. Oh, okay. We have to let them fall. Okay, so we have to have them fall. And what we can do is have them fall in order. I wonder how this day is progressing. Okay, I've already 150 people done. Yeah, so we let them fall in turn. I forgot about falling. This chair, always spinning without permission. So we have their starting. Transform these coordinates. So here we have them by min. And we could take each of those in turn, each level, and then have them fall until they reach a thing. And I suppose as they fall, we can also build the adjacency graph. Yeah. So we search for them in order. And then, yeah, let's search through them in order and have each of them search through all of the settled bricks. So this is like an n squared thing. Search through all the settled bricks. But one that overlaps its area. And then the highest such brick. So let's define a fall function. The highest such brick. Okay. The fall, we're not gonna do anything clever here. So we have our coordinates. Brick. This is an area and a depth. Yeah. And we'll just give that type of name. We should just make that case class, shouldn't we? We should, but we won't right now. It'll be an easy change when we get to it. Settled. And this is going to be what? A list of bricks. Yeah, let's do a linear search through these. List of brick. And then we have a new list of brick. And let's say settled is sorted. The highest is on top. Okay, what is all of this? I don't like all of this. This is way too much shit. Copilot, you are very drunk. Yeah, so we'll call this like A1 and B1. And we could take settled dot find, or let's do collect dot. Wait, find gives us an option. That's fine. Case A2D2 such that A1 intersect A2 is not empty, yes. And not quite true on the D1. In fact, the D1 doesn't matter. And we're gonna do a map here. Uh, so we're just gonna take d2.max plus 1, right? Let's shorten this. So underscore 2 dot max plus 1, and then getter out 0. So this is a new bot val. And in fact, we could just return a new brick here. We can cons it on somewhere else. I don't know. Instead of the left parameter, because this is looking like a full left kind of thing. Plus new bots. Yeah. Do d1 dot size, or what we could do here. Is it d1 dot size minus 1? How much did that fall? We could do like, we could phrase that in a different way. d1 dot max minus the difference between, okay, d1 dot size plus new bot. Okay, yeah, and it is minus 1. So let's say until. Oh, my keyboard is disconnected. I've been having those issues lately. Outside of AOC, do I do leak code questions? Nope, nope. I don't think leak code's that fun. Then what we return is A1 and new depth onto the settled pieces. Right. And then now we take coordinates and we sort them. I don't think they need to be indexed, really. I'm just gonna call them bricks here. I'm just gonna unzip so other things don't break. Val, ignore the indices, bricks equals coordinates dot unzip. Bricks dot sort by their bottoms. So bricks is a list of an interval, yeah. The depth dot min. And then I guess we can fold left here and fall. Exactly. Okay, so now we have all of our bricks. And by min can be defined in terms of this. Right? But we can just do a count. Bricks.count. N squared. Is an N squared thing here fine? Yeah, let's do that for now. And then we can make graphs later. I think n squared is totally fine. So we're gonna count case case A and D. What do we want with that? Something similar to what we have here. Um, Bricks that exists. Case A2, D2 plus 1. And is this not? Oh wait, it has to be the only one not supporting anything. Let's make the adjacency graph first. So I think our first iteration of the answer basically is looking for things that aren't supporting anything at all. But we also want the bricks that are one of two supporting something. Let's just draw this out so we know what we're thinking of. So there can be some sort of stack, yada yada. Yada yada. These two can be supporting the same one. This can be supporting that, etc. This is disintegratable. No, that's not disintegratable. Maybe this one is disintegratable because it's not supporting anything. This is disintegratable because it's one of two things supporting something. So I guess we need a map of things it's sitting on. Like this is sitting on this is sitting on this. So if when we're deciding if this brick works, then we check like I guess we check the level below it and check, or we can check what it's supporting and do accounts on what it's supporting. So if it has any brick that is only supported by a 1, so we have the adjacency graph and then the reverse adjacency graph. Yeah. Okay. All this old stuff, let's comment that out. We're not actually using that. Val sorted bricks. Okay, so we have sorted bricks. And I suppose if we take combinations, it will preserve the order. Sorted bricks. Let's zip them with index. We have them indexed. Maybe we just need a count of bricks. And then we take combinations, and then we have adjacencies. Let's give them indices. Dot zip with index map swap to map. To so something like this. I want great. This other code is not quite right. When I make the bricks, I should also just make the adjacency. I should just straight up make an adjacency graph as they fall, shouldn't I? Right, if I did this on No, I'm just gonna iterate through them again. But we've already done that work. We need this work exactly. Okay, we're gonna define a fall too. Um, um, and we want adjacencies. I guess a brick here is gonna have an index. Why is it hard to understand functional programming? I wouldn't say it's hard to understand functional programming. It's just different. If you've done imperative your whole life, it's going to feel very foreign. But for people who've done like math all their life, instead, it's going to feel a lot more natural. Lo-fi Tetris theme. Um, you know what? Not a bad idea. Let's put that up real quick. Hmm. And we'll just let autoplay from there. Okay. Do we do we want indices? Do we want indices? Can we just have the bricks in there? Yeah, we don't actually need the indices. We don't need to like reference them that way. So this version, this does a map from brick to a list of bricks that support it. Yeah, let's do that. Here, we'd only found one, but there might be others at that depth. Um, so I guess this becomes a filter, except we need to make sure, well, yeah, we find the first one, and then it gives us our new bot. And then I guess we use that bot to find bricks. Dot filter. Um, dot max. I guess I want the max of it. And then the max plus one equals new bot. So well, supporting. Yeah, this can be made a lot faster with like indexes and maps and such. But that is not the way we're going. Wait, map. What happened here? Um, whoops. So we have dot underscore two dot max, yeah. And then we have a new depth. So A1 dot new depth. And I guess that points to supporting blocks. And then we cons that onto settled. I guess we add that to settled. So this will no longer be sorted. It's probably fine. And then we turn a map of brick. Okay, we can keep our old version there too. Do we care about stored bricks anymore? Yeah, so I'm gonna do this thing here. Now we fold left with a map that empty, and it goes from brick to a list of brick. And I don't know, that could be a set of brick. And val brick supports. So any brick that has multiple supports and any brick that doesn't appear as a support. Okay. Um, that works, that works. So it doesn't work to have like a set. Well, no, the brick coordinates are unique. Right? They might have the same shape or whatever, but their coordinates will differ. So oh, it's not any brick that's supporting that's part of a set. Because it might still be supporting another brick and be the only support of that. So I want to invert this. Um, so if this is the supports of each brick, then we have supporting. Well, supporting, it's also a map from brick to listed brick. And it's not going to be that. It's going to be supports dot to list dot flat map. Supporting the map. Yeah, that's brick, sure. And so brick to supporting, it becomes supporting to brick. Wait, supports of a brick. No, this is what is supporting that brick. So given a brick, it will tell you what bricks support it. So these are supporting brick, and then now, yeah, supporting tells you what bricks. Wait a second. This is a brick to the things that is supporting it, not the things that it is supporting. I need a better name than supporting. So supporting is ambiguous. So let's name this above. Right, these are the bricks below. Yeah, let's make that very clear. And then val, this is just gonna be the full below map. So given a brick, tell me what's below it. And this can be the above map. And we gotta take below to list map. So there's a brick, and these are the below. And now, I guess our brick is the above now, right? So above goes there. Code's right. It was right. It reads better now, so I don't get confused. And then after we have all those tuples, we turn this into a new map. So let's go back here. Dot group map. Um, wait. Okay, here. Okay, we have a bunch of bricks. Say these bricks dot map to the piece above. Cool. How's bricks defined? Bricks dot view list. Sure. All map here. Okay. Now, I guess we could take bricks that are above. For every brick, we look at what's above it. We keep the bricks. Take me too long. Okay, so above dot filter. And they're gonna be a bunch of belows that are not being supported by anything. Or bricks that have nothing below. Bricks that have nothing above them are fine too. If nothing above them, this is not gonna show up here. So we can get val leaves. Below. Yes, so we shake. I don't think it's quite that. So these things will have something below them. Yeah, I guess we can take the keys. Below below that key set. And we diff above that key set. Okay, yeah, that's right. And then val redundant. What are we gonna do? So we could look at what's above a piece and check if it has any other. So above dot filter. So we have a brick. We have an A above. Oh my god, I hate that. I hate that's an unfortunate name I've given to my maps. Um, so above, and we need to check below of above. Below of above. Dot size is greater than 1. Yes. And then we return this brick. So I'm going to turn this into collect. The case if blah, 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 we just return that brick. And oh, wait a second. So we filter on above. I guess if all of them that are above it. So if above dot for all, then below that dot size is greater than 1. Man, that is confusing to read. I'm gonna refactor this. It's gonna look, and then it turned out it's like way simpler than making it. So leaves. I guess we might as well union them, but union, redundant, that size, val ends one. There we go. Wait. Okay. View list. Now this is a list from area to, of area and interval. List of bricks. And was Lisa set? I guess we could two set that. Are there other issues here somewhere? Underscore two. Yeah. Monotype. Oh, yes, it's a brick to a list of brick. Other issues. Found A2. Oh, wait, what is A2? What is D2 then? Depth. That's a list. Oh, yes, settle.find. We need to ignore. We just need the left side. We don't care about the list of things it's supporting. You know what we're going to do instead? We're going to do cell.keys, that's a list. And oh, it's not going to be sorted, is it? So we can't do dot find. We could use a sorted map with an ordering on brick. Or I suppose we could use a list and then like two map this at the very end. Yeah, okay, let's make this cell is not just a list of bricks. That's sorted. I know there's a much nicer way to conceptualize this. And it's probably going to be a lot more concise too. But we'll get there eventually. So we're going to do this and then that to map. And start with a list.empty of brick to list of bricks. That works. That works. What's going on here? All map. What is it not like? Oh wait, this is still saying map list.empty. There we go. Too many type arguments for a list, of course. What's wrong with this? We found this brick to list of brick. Yeah, that's cool. That's what it should be. Or wait, why is there an or? Oh, it's because we're doing a plus here. I guess we're back to consing. Yeah. So settled, we can do settled.find A2, D2. We're still gonna need to ignore the list of bricks. I don't believe that. What is settled? Settled is a list. Oh, hold on. There it is. The missing parens in the tuple. I've implemented this so much. We're gonna map underscore one, just the one brick itself. We don't have to do this. And now take depth.max. Is below a list of bricks. Do this up here. Is there design patterns in functional programming? Yes. Yeah, all sorts of design patterns. And a lot of the old Gang of Four design patterns. I don't know, like the visitor pattern or whatever. They're just functions now. You stuff like map and filter. Yeah, you have interpreter patterns, type classes, monads, whatever. Final tag lists. All of it in Unity. Awesome. What am I doing here? Man, I'm being an idiot, but I don't like 1/factor. So that works. So we have leafs and we have redundant. There's only 7. No, this is for the example. This is only for the example. And that is patently wrong. 5 bricks. 5 of these bricks can be removed. Okay, let's look at what are leafs. Do leafs for each print line. This is probably why I wanted to keep an index attached to these. It considers everything to be a leaf. Okay, so my leafs are not well defined, but how many are redundant? There should be a list of 2. Okay, let's check our adjacency graph. Let's check what's below each. Below for each print line. Oh yes, everything gets processed. So everything does have a list of things that are all below. Right, the things that are on the ground have nothing below. This 0, 0. This 1, 1 should have an empty list. It should have this thing here. Okay, so we have our settled bricks. You know, I liked it when I was doing this and just basically sorting them. And here I thought, oh, let's just turn it into an adjacency graph while we're at it. Because we're basically already doing that part. And then return what is below it. So breaks.filter, max plus 1 is equal to the new bot. That's not quite true. Max plus 1 is equal to the new bot, and there's another condition, which is that I filter this way. The dot filter. Um, so the intersection of their lateral areas is non-empty, and d2 dot max plus 1 is equal to the new bot. So those are all the bits below. Oh, hold on. It's not the d2 dot max. It's a new d2. It's a new bot. I guess we have to have a new top too. Let's do this. Val new top. New bot plus d1 dot size minus 1. Right. And now we find all of these where I guess we'd already found one. Now we want to find all of them that intersect at that level. Let's let's put this check first. Going to be a simpler discriminator. So d2 dot max plus 1. Oh wait, this is filtering out the old bricks. Oh yeah. This is fine. We didn't need to define a new top. But let's still put that first. So all the bricks for which it's max plus 1 is just a new bot. And then the intersection is non-empty. And then we have a new depth. And then we track all the things below. We want to list that. I mean, so that's fine, right? We didn't change anything. What was wrong with it? Let me make this full. We sort them by their bottom ends. Which one needs to be considered fall first? All of these end up being above an empty list. Okay, what are the bricks I'm passing to it? Wait, when we unzip this, we get like an interval. I'll just make that a 2 list so that brick stays a list. Bricks for each print line. I think I should rewrite some code because this is hard to handle. I really should. And I'm really like falling behind. How many people are 1,000 people are done with part 2? It's like 2,000 people are done with part 1. We're very close though. Let's see if we can make this work. Let's take those bricks. Look at these bricks. I don't know why it's not running. It has issues. Filter's not a member of any. Oh, wait. Settled. Settled. Dot filter. And below, we required a list of brick. I guess I make this a collect. So we'll turn this into like an if. What is settled? There's more to this here because there's a list of things below that we don't care about. So B at there, and that B is the thing we're returning. Okay, there's now a list of bricks. Oh, yes. Okay, we have to. Okay, bricks for each print line. These all look fine. There are none of them on the ground. So what happens if we find nothing? If we found nothing, it should be a getter else 0. Oh wait, yeah. So a bunch of these are floating. So some of them are floating at like the 1-1 range. I guess none of them are at the 0, right? If we look here, none of them are at the 0. So after we do below.keys.toList, that sort by their bottoms for each print line. Okay, this will give us an idea if that settling worked. So we have one on the bottom, we have B and C sitting on top of it, and then there are these D and E. Okay, so that looks good. For each, let's do another for each print line, and this time we'll just print these in order. So for each brick, we're gonna print what's below it. Print line B to below B. How does it know what I want to print? Okay, so this one on the bottom has nothing below it. This one has that A below it, etc. Okay, this one has a 1-1 below it. This adjacency map looks good. I don't know what was wrong with it. And let's take a look at above then. So we just invert this map basically. Above for each print line. Oh boy, hard to read. But none of these have an empty list. I guess this has an empty list. Okay, let's do this. Above that map, map values, and then we'll get the size, the number of them. Okay, so 1, 2, 3, 4, 5, 6. The ones that don't appear in above have nothing above. All of these have things above them. All these bricks apparently have bricks above them. So my above is wrong. Wait, ends 1 is now just 5. Wait, is this perhaps working? Should I just try this? Yeah, just try this. We're taking too long. 448. Okay, too high. Ah, it's the right answer for someone else, so we're close. 4, 8. too high, right, for someone else. Okay, let's go back to the example. And we should get 5, but we should get it in a slightly different way. I wish I had names for these. In fact, you know what? We can give them names. Val names equals whatever the sort by thing I'd done. Below that keys, sort by, yeah, that zip with A, B, C, D, E, F. Right, there's 7 bricks. E, F, G. That to map. Now we can print their names. So like this thing here, you could print the name of B. Below B dot map name, and this just becomes name of B. There we go. That's name. There we go. So A, things are below it. Okay. This is correct. So now we do something similar for the above. We'll do above dot. We'll sort them in the same way. Actually, you know what? Yeah, we can use below keys because they are all going to show up in there, right? Because they're all just pointing to what's below. So name would be to above. Um, Get or else nil. That'd be map name. Above B, get or else nil. Map name. Here we go. Oh, hold on. I guess we do like a get here. Get or else nil, sure. Okay, these are things above A, right? B and C are above A, D and E are above B. D and E are also above C. Cool. And let's say leaves.map names for each print line. These are things that are not supporting anything. And it's just G. What is it? It does not support any other bricks. It's the only brick that does not support any other bricks. And then redundant, map name for each print line. Redundant is not defined yet. Okay, let's move this down here. B, D, E, and C. Right, so B can be disintegrated because the brick's above it, D and E. C, D, and E. Okay, so I have the right, yeah, that looks good on the example, and I get the right answer. So what am I missing in the full input? Day 22 going? Well, my head hurts too, but not because of the problem, but because of my code. This is too much code, and I hadn't been thinking about I hadn't been thinking about it properly as I was writing it, and now I'm doing things in a more complicated way than they need to be done, which makes it harder to continue developing. No such key exception. Yeah, I guess if you don't find anything. Wait, wasn't this fine? Oh, wait. It's failing because we don't have names anymore. We can just comment those out. All the usages of name only applies. So 448. You know what? We're gonna go back to uncommenting those. And what we're gonna do is for names, we're just gonna zip with index. Yeah, zip with index. Okay. So now just remove these. Leafs, and those are the redundant pieces. Where are my... Okay, this is our check on belows, and this other one's our check on aboves. Okay. These are things that are below each. So I assume like 0 through 18 are on the ground. Right, so let's print the name of B, and B, I guess we'll print the interval 2. B is a brick. The underscore 2 is it? Oh, hold on. I guess you have to add a space here. We're inside an interpolator. Yeah, those are all on 0, right? 19 is supported by 14, which is on the 0 to 0. I wonder if anything is supported by 13. We have our adjacency graphs. We have a reasonable way of searching through this adjacency graph. It's possible that we're missing anything. Let's do like below dot size and input dot size. Is in below. Not everything is going to be in above. Above dot size. Right, and that's exactly why leaves can just be different union of keys. Four, 4, 8. That is what I tried, right? 4, 4, 8. Leaves dot size and redundant dot size. 320 plus 128. That's 448. They are disjoint, as they should be. Uh, it's below, whatever. I could do something like this. Um, that for each B, we're gonna just get the name. Print line. Yeah, we'll just do the name of B. And then B itself. Hmm. And let's explore the output. Wait, what's this print line here? Uh, Name for each print line. We don't need to print all the names. If we look at one of these randomly, will it look fine? 1029. So it's above 1029, which is above. Wait, how can 1029 at 107 be above nothing? That seems weird. The 1029 is this with range 131, 131. So that's its height. It is below 1022. Of nothing. It can only be above nothing. Let me just try I wrote above and below properly here. Um, just rewrite this a little bit. Add in a new line. 000 is below. Oh yeah, this should be named as above. And the other one should be named as below. That'll make more sense. It is below. I hate my naming convention. That's one of the things I really hate about my code here. I don't know which way my adjacency graph goes. Okay. So let's look at 1029 again, for example. And what is this line? Coordinates for the next two. Yeah, I don't want that printing. Just delete that comment for now. Okay. 1029 is at depth 131, 131. What is this? Names? I don't want that printing either. 1029 is above 1022, but is below nothing. The 1022 is below 1029. 1022. Okay, and like for each of these, we could print like a chain. So if there's a bug here, it's a subtle one. And I'm not going to find subtlety in code that looks like this. Maybe I do a cleanup. Man, it's unfortunate to Go away all this code though. Uh, yeah, below gives you the things that are below it. Right, I tried 448. It was someone else's answer. So I'm missing just a thing. Um, Maybe I'm missing something in the rules here. Assign each brick given a letter. Um, okay. Z-axis is the x-axis. And this is what we see. G, F, E, whatever. This is before they've fallen, I suppose. That looks like this, sure. Huh. Don't actually disintegrate any bricks. I guess part two is gonna be like, what's the fewest number of bricks you can disintegrate? I don't think I'm missing anything. There's no fancy rules about something that would not. Comment out this code, so I'm not looking at it. Yeah, we have a bunch of cell bricks. They're like in order. And we're like folding left on them. We show, so these bricks are what's settled. We're using fall map on these things in order, right? We sort them by their bottoms. And we have each of them fall. And when they fall, they get added to the map-ish thing here, which preserves their order. Um, and, and bricks. This is the main algorithm right here. Nothing else is all that complicated, right? Below is defined using the algorithm. We sort first, and above, we just take all of these and we swap them around. Yeah, and then we regroup them. I guess we could make like a secret ground brick or something. Or if this is empty, it gives it the ground. Oh. That'll just confuse us in other ways. Do I like, do I draw a tree? Um, this is too much information. I can't find a bug in something this big. I need to make examples and smaller test cases, right? And look for a test case that fails. Oh, but making these examples is like really annoying. Um, it's redundant if there is more than one below the brick. Okay, these are all bricks that are above something. Oh, it might be a bad thing that we're doing this for bricks that are above something. We could do this in the other order to calculate the redundant. It's more likely that that's wrong. Above doesn't have all the keys. Okay, let's do this. Just comment out this older version. And let's look at all the bricks. Let's look at all bricks. And in fact, let's just look at them sorted, the same kind of thing. What is this printing? I don't think I want this. What happened to my nice prints? For each. Yeah. This is not useful. I'm gonna comment that out. For each print line. Comment that out too. And these things. In fact, we're gonna straight up delete them. Okay. Go look at all the bricks, which is gonna be like the bricks.keys. Below.keys. Yeah. I mean, I guess it can only be redundant if something is above it, right? So we look at the things above it. So these are all the pieces that are above that brick. And we check that all of them have other support, other supports. It's pretty straightforward, except for like my dumb naming convention that makes it hard to understand. This is totally fine. But like when I read it, that's cool. We could also look at everything that's below something. If it has multiple below it, let's redundantly calculate redundant and check that they are the same, right? Let's just say this is redundant too. And we're checking keys are below. And we have case, brick, and the bricks below it. If bricks below, I wonder if I'm not making this a set. I think we need to call dot distinct on this. Let's do okay, redundant dot size. Some of these might be doubly redundant. Redundant dot distinct dot size. First, we're going to filter out bricks that have anything below them at all. I guess this turns into a flat map. Let's start with a filter. Um, if bricks below that size is greater than 1, or rather, that is the right side of our arrow. Um, and now for each of those bricks below, I guess we map to underscore 2. So we're going to flat map. So these are potentially redundant bricks. They might be redundant amongst themselves, so I'll check distinct. And I guess I check that they're not supporting anything else. That filter. No. This isn't the case here. So this is just a brick. And they are not supporting anything that's only supported by one piece. Oh, it doesn't really work this way. This is my only way here. Right, these are potentially redundant bricks. Because it has a neighbor supporting something else. I need to make sure none of the things it's supporting has other things. We basically write this code here again. Yeah. Okay, and the leaves. Look at all these leaf sets. Let's see what they're supposedly above. Oh, we do print all the leaves, don't we? I'm gonna take these. I'm gonna filter them. Hello. Yeah, let's comment all of these things out for now. And all we want to see is the leaf keys. Check what's below them. Or, yeah, check what it is above. I want this line here. Below keys dot intersect with leaves. Keys set. Okay. Oh, some of these are above something. Oh, yes, of course. They'd all be above something. Because they're leaves. But we actually want to check if they're below anything. The below key set that intersect leaves. Right, it's always empty list. So, unless it's like my falling thing that's wrong. I mean, this has to be the place where there would be a mistake, right? Um, so these settled bricks are sorted from top to bot. These are sorted by their tops. Or they're not sorted by their tops. Because originally we sort by bots, and then we have things drop. I think we. Oh yeah, yeah. Trying to do this with find is too clever. We should just filter through all of them. This here could end up being the wrong value for a new bot. So we need to find. We need to do that filter and max by height. Start with the filter. Dot max by height. Oh, yeah, exactly. Okay, let's see if that changes our answer. Okay, max by. So we filter this. I hate that I'm using all these underscores. It makes it hard to read. Okay, so this is an area interval. I guess I could map and then max option. Okay, we map to where they would be. Dot max option. That getter else 0. Okay, does our answer change? 430. There it is. I found it. I found it. Hi, Nicole. Oh, we need a chain reaction. Figure out the best brick to disintegrate. How many other bricks would fall if that brick were disintegrated? Okay, we could do like a memorized search graph. Um, if we had this below graph, right? We can filter out loose and redundant. We could start with that. Um, what do we do? We take all of our things. So yeah, we could take below dot keys. So diff leaves diff redundant. That's too set, I guess. We could look through adjacency graph, look for things that are only supported by 1. Well, okay, that might not matter because everything that supports it might be in turn supported by another thing. Let's look back at our drawing here. Okay. Okay. This one, we could see it very visually. This would drop that and that and that. Um, search everything from the bottom. No, we want some redundancy here. We're like, once we calculate what something would drop, yeah, we can just calculate what everything would drop, memorize it, and then we would do like a would drop recursively. But how do you handle? Okay, how do we handle something like like this. So we can say this would drop this, but that would in turn drop this. I guess we'd have to drop both of those. And look at what was supported by them. Yeah. We wouldn't be able to look at what was dropped by them because this would drop nothing, right? So memoizing doesn't help there. But if like this is so we have a DAG. We topo sort this and go in that order. Then first we have this, drops this and this. Then we look at what they were supporting. And we need to check that that thing that was supporting. I guess it helps that we have this. We already know which ones are redundant, right? This could be supporting something else that's supported down here. So this wouldn't be dropped. So do we take like the union of what they were supporting? If we take the union of what we're supporting, we're going to take this as well, which is too much. If we take the intersection, it's just going to be this. And we're going to ignore this here. Is knowing that they are redundant help. This. I guess we have to look back in our other adjacency graph for each of these bits. So we could take the union, and for each of those, check if they had supports other than this. So we diff this out from their supports. So we look at the above graph. Oh, I can't remember. I can't keep track of which map does which. So the below map points to things that are below it. Right, this will have nothing below it. And I wonder if we did this from the other side. I mean, let's say we did it with the below graph, right? We start here. Basically, we could say like, oh, if you took out this, we would be down. But if it's supported by 2, I don't think we want to go that way. So for every piece, we look at what's above. We take the union of all of the pieces that are then above it. So yeah, let's work with our these are all the things that would drop nothing, right? So we don't worry about those candidates. I guess this is an unfold to the full set of things it drops. And if we're doing this sort of like recursively or like memoizing, then let's say, well, okay, if we're searching from the bottom, that doesn't matter. So we start from like a bottom point, like this one, look at what it drops, and we have that set. Then we go here, we look at what it drops. We do a search all the way up. Thing is, that search could get pretty big. Okay. Yeah, I want to be able to, like, what if I search from the top? Searching from the top is not ideal because, well, we could still know. So let's say this is part of a bigger tree, right? Things are supporting it, whatever, right? If we already know what hitting this drops, then instead of instead of looking through recursively, well, we might still want to look through recursively because this is not going to be part of what it drops. Right, this is not going to be part of what it drops. Am I optimizing too soon? Right, like if this is also connected to this, then what we'd have memoized is like, oh, these would drop and this would drop. Um, so the memoization doesn't help us because we look ahead. Um, this would drop too, and it's not caught by either of those. And again, that's if we start. Yeah. Oh, yeah. Those would only be memoized if we start from the top, and we're gonna start from the bottom. I think we should sort them by their tops, right? If there's a big block supporting things that could potentially be supported by other blocks, then we don't want to see what happens if that is removed first. We want to see what happens if this is removed first. I'm just gonna do it. And I guess for each candidate, we have to search the tree. Okay, F drops. We have some brick B. And then we have a list of, I guess at this point we can just do a count of bricks. So we can just do an int. And then we look at the bricks below. Um, union, what's below them. So below B, I don't think we want to do this recursively because B might be a redundant piece, right? If we're going recursively, then one of the things we're looking at recursively might be redundant. And the drop count of that wouldn't matter. So below B dot map, the things are, oh, actually we want things are above B. Above B and map above. And we check which of those that are above. Maybe what it should return is a set of bricks so that all the redundancies can be sort of merged together. Those bricks get dropped. And then now we need to say like, oh, these are dropped. What else is going to drop? Okay, so we have a set of dropping bricks. Suppose we have a set of dropping bricks. And in this case, that'd be like the things that are above B. The things that are above B that are not supported. Yeah. I guess we could check that B is not redundant or not. So B is not redundant. So everything it supports is not supported by something else. So all of the above would drop. And then now when you drop all of those, some of those might be redundant. So let's say we filter by the ones that are not redundant. Hmm. Okay, let's have a new tree here. Oh, here's our root node. Here's a root node. Let's have two root nodes. We know that this is not, maybe we'll consider things that are not redundant, but this might be linked to something that is redundant. So let's say this one is one that's not redundant. Then, yeah, I don't think I need to worry about performance. I need to worry first about just getting code that works in the first place. We would have that this is redundant. And if it is redundant, we would check if the rest has been deleted as well, the rest of it supports. So maybe one iteration through, we have this, right? And then we take everything that's above all of these. So we'll take these. So we know this is dropping. We know that these are dropping. And then for each of these, we have to look at what they are dropping. And if we know it's redundant, we need to check if our dropped already list contains whatever. Okay. Oh, yeah. Well, thank you for sticking around, Pet Alligator. I appreciate it. Okay. So this eventually gonna return an int, but we're gonna do like an unfold. So, or yeah, an unfold, and then we'll take like the union. So, iterator.unfold dropped. So we have a set of just B. And then this can be our our thing that's been dropped, or all of our things have been dropped. And dropped dot map, we want to check things are above it, or rather, we want to partition this. So dropped dot partition. Yeah. And we'll partition by redundant. So we have B's and R's. Oh wait. We're done. Let's go on the left. So we have R's and then we have our B's. And then to determine if R's is dropping. I guess we have two sets, dropped already and dropping now. So set that brick and set. So we have dropped, and then we have our set of things that are dropping. Um, I guess our return might not matter. So these R's plus B's is our new dropping, right? Wait. So, new dropping is going to be is B's and is whatever is above B's and above R's that have had the others dropped already. So B's dot map to above things are above B, each of those, and R's dot map above dot filter. So for each R RA below RA, things below RA are either contained in dropped or dropping right now. So dropped. So yeah, we want all the things that have their below already dropped. So all of them. The below RA dot for all. BRA. Dropped bra or dropping bra. Okay. It might have a support from like well below has already disappeared. And be our new dropping. Well, new dropping equals that dot union that. Okay, and then our state val new state equals dropped dot union dropping. and then the new dropping. Hmm. And what even are we like returning in here? I suppose at some points when this is just empty, we just return all of the dropped. So I'll make this a recursive function instead of whatever I'm doing here. Def search. Yeah. So we have dropped set of brick and dropping set of brick. And this will return a set of brick. And then we do all this code we had here. And if dropped, if dropping that is empty, then we return dropped. Else we do all this stuff. What's the issue with this? R's and B's. How's that recursive value? I don't think we know what we're talking about yet. Now this new state actually just becomes the whatever new search. Search that. Found. Oh. Okay, let's look at the definition of redundant. We make that. To set it. You don't have to keep this, right? You do set it basically every time. Right, we want to know which things are above, so RA, which of them are dropping. R is dot map of, I think we want to flat map that. We're looking at everything above it. Right. I feel like these should be sets. We at least need to take distinct. Okay, so for each of these above, it's a single one. Then we check that below RA for all. Right, okay, if you flatten above, it's already a set. Cool. RA, object and equals. Wait, where's that flat map? Above. What is okay, let's map it to a list of bricks. So now this is a set of a list of bricks. Flat map this with above to set. And what's the value of this, or the type of this? This is a set of bricks. And it drops if for all, if everything below it has dropped or is dropping. Has an issue with this. RA is an object and equals. That makes no sense. Okay. Above. We'll call this RAs. This is a set of brick. We'll do RAs that filter. Set of list of bricks. Wait, if you do any filter, this is not my best night of coding. Okay, you check that for all. And this whole thing needs a set. Surely foo. Foo is a set of bricks because it's just a filter in RA, right? It has an issued foo set of bricks. Where does a list of bricks? Oh, wait. Up here, we have to flatten up above too. I see, I see. Because BS is a great. I misread that error message the first time. Great, so that compiles. And now we search set.empty, set B. Let me take the size of that. And we could try this for a random brick. Wait, are there other issues? Stormy weather, huh? Last day for kindergarten. Solving it's going okay. I'm just not a I'm not a coder tonight. I'd be too tired. Distinct is not a member. Wait, not distinct. We call this someone we don't need it. Oh, right. Okay, and then just take a look for one of them. See how many drops. Candidates. Dot to list dot head. And how many drops do we get from that? Key's not found somewhere, of course, because above doesn't always have. Above does not always have keys. Above should default. You know, where's above defined? Not get or wait, no. With default value nil. Okay, so this one drops 12. Let's just do candidates dot map drops dot max. Oh, 1095. No need to worry about optimization at all. 1095 is too low. Let's try this for the example. What we get? 7. Yeah, because taking out A would take out the whole thing. Could add a brick that's supporting something else to the example. Integrating brick A. Oh, we can do that. So we had them sorted, not sort by somewhere. One of these. We could check the values of those. Just pass the sort by. I don't know what to call these. We'll just call it B's. B's 0. How many drops do we get from that? That's A, right? It would cause all other 6 bricks to fail. Wait, how many bricks are there? There's 7 bricks. B's that size. Wait, why is B's that size? Oh, hold on. We did this intersect. So I'm just going to do B's that to list. There we go. Yeah, A would drop 7 of them, including itself. In this example, the number of other bricks that would fall as a result. Okay, A. Let's just do this. BS dot indices for each like a map. Map drops of I map drops of BSI. And then for each print line. So there's a 7, 1, 1, 1, 1, 1, and then 2. There's a 2. It drops 1 other. Wait, am I off by 1 in my answer? Should I give? I need to figure out the best brick to determine how many other bricks would fall. Technically, I haven't determined how many other bricks would fall. I determined how many bricks would disappear. The number of other bricks that would fall as a result of disintegrating each brick is 7. Was the sum of the number of other bricks that would fall. Oh, okay. Okay, so we do this dot size minus 1, and we just want the sum. So we want dot sum, and that is our answer. And the sum there is 7. Okay. I don't like how I named this file day 22 cleanup, and I haven't actually cleaned it up. 1232. 1232. 1232 is too low. Okay. 1232 is too low. We do get the right example, right answer on the example. All the others cause nothing to fall. So yeah, we look at the candidates. I guess that's part of why I thought, like, if you have to do this for all of them, then there's no point optimizing there. Well, we would just reveal what actually gets dropped. Since it's returning the int, we can return a set, a brick. Wait. 1232. I did the wrong thing. Okay. Change that back to int. I pasted in the wrong thing. 73059. It's right there. Okay, 73059. 73059 is too high. Okay. 73059 is too high. Is candidates a set? It's a set. Okay. Candidates set. Iterator map drops dot sum. 78164. Um, 78164 is gonna be too high. It just got higher. 8164. I wonder what these values are. Let's just print them for each print line. Oh, 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 oh. Yeah, I mean, sure, these all drop at least one. A string at that's not going to help me. bs.indices dot map. Yeah, BS is just all the bricks sorted. These are their names. Let's do B. Let's show the index. It should be the same as name. Name of B on BSI. Yeah, make sure that's actually the same. Oh, it's not still in scope. This. Okay. While we're checking, let's just do a for all check real quick. Just making sure the indices match the names we've given them earlier. Map, or for all, I equals name of BSI. This should be true. I'm just gonna search that and then leave it alone. That was a side quest we didn't really need. Okay, so this is all the bees, not just the candidates. We just want to do candidates. Candidates map, or for each candidate, we're gonna show. We got print line. So the name is C, the thing itself, then how many it drops. Maybe I don't show the thing itself just now. That little bit of code right there took way too long to write. I'm just way too tired. Are there other issues with this here? Let's just run. Okay. 970 drops 11. We could look into one of these. Like, 210 drops 974. Um, we can do some property-based checks on this. So if 210 drops 974, we could look at everything above it, count the drops on each of those, and it should be greater than or equal to whatever this drops. Let's do a candidates dot for all C. We're gonna do an insert drop C is less than or equal to um, things above C dot map drops dot sum. Iterator map drops dot sum. You want to be careful about hold on. What's the issue here? Unit required boolean. Oh, yeah. You don't need to do multiple asserts. Just check if it's for all. Ah, okay. Well, let's find one where that's not the case. Candidates, let's find where drop C is greater. Wait a second. No, that's not necessarily true. Right, for example, maybe like everything above a B is well supported, except one thing. We drop one thing. When would this drop? Okay, wait, so let's draw an example here. So this here might drop a bunch of things, right? But those might all be connected to the same thing. So none of those would drop anything. But that's not a property we have about drops. Right, this would drop 5, each of those would drop nothing. Yeah, so some of the drops, if you drop just the whole thing, if you dropped all of them, that's not going to be a useful check. We need to look for other discrepancies. Oh, this is not even a true thing. Everything below it, if dropping something would drop a lot of things, then everything below it should drop more things. Right? No, not everything below it. Again, like dropping this could drop a lot of things. But this could be supported by multiple things, right? So dropping either of those wouldn't drop more things. But we could filter everything that's below it and redundant and not redundant should drop more. So C. So below C, that diff redundant, filter not redundant. So drops of that should be greater than, or it should be strictly greater than whatever C drops. Okay, wait, hold on. So we map drops dot sum Filter not redundant. Map drops dot sum. Is false. Interesting. Why would that be the case? Um, let's filter for those cases and take a look. But surely if this is not redundant, right? So everything that supports only supports one thing. Let's just delete this line here. Yeah, actually the one thing below it, I guess. Yeah, if it's not redundant, there's only one below it, right? We check that. If redundant C I guess we can XOR this. If redundant C, then below C dot size. Wait. We're looking at things that are below C. Below C dot filter. Oh no. If C is redundant, so let's do a filter. And it's not. Oh, yeah. Candidates are already not redundant. Why would this be false? So everything that's below C and is not redundant have only one thing below it, right? This is an obvious check, but we can do that. So everything below C not redundant, but for all below, that size is less than or equal to 1. Those are not redundant. I guess we could filter for, no, the redundant ones are going to have 1. Redundant. Oh, no, redundant is going to have greater than or equal 1. Or greater than 1. No, that's still false. There were edge cases. Oh, wait. There's things in the ground. Okay, filter. So the things that are not redundant. Okay, what was this check I was running again? So everything supporting C that is not redundant. And oh, I guess one check I was doing was if there's anything that's not redundant. So if anything, if below exists, if there is a redundant one, then then below C dot size is greater than or equal to 1. Else below C dot size is less than or equal to 1. needed then. This is false. But wait, if below C, if there is a redundant thing below C, there is anything that's redundant. Oh, it could be redundant with another piece. Okay. Right. Yeah. Okay, yeah, that's fine. So we're checking. So this is fishy. This is fishy. So we're looking at all the ones that are not redundant, and dropping them should drop this and everything above it. So let's find this case. Candidates that find a C such that drop C is somehow greater than let's do this. Below C that filter not redundant drops. Hold on. If you map the drops for all of them, yeah, okay, we'll just find a C such that the drop C is somehow less than or equal to the sum of dropping everything that's below it. That is not redundant. Here's an example. Exactly one example. And I wonder what's above and below that. Let's get the name of that. So that map name 970. So what is above 970? Yes, bricks 970. The sorted bricks. B's. Okay. Let's look at B's 970 itself. And let's look at what's below B's 970. And 7, 4 to 6, 100, 100. There's only one brick above it and one brick below it. And then this is C such that dropping and below it. So how many drops does 970 have? Drops. Oh, this is like a zero case. Okay, dropping BS 970 results in 11. Let's see what happens when we drop the one that's above it. So drops the thing above it. We'll just do a dot head. Dot to this dot head, I guess, because that's the set. And then below it, dot to list dot head. So dropping the one above it drops 10. Dropping the one below it drops 12. Oh, I mean, that's fine. My check is wrong. Equal to. Okay, it should be the case that for any candidate, dropping is, oh yes, for all these candidates, dropping C should be less than dropping everything that's supporting C. dropping any non-redundant thing. Drop C. So we drop everything below it. Oh, wait. Again, we're here. We're here. If you drop everything below it, each of these would result in 0. Might not be a thing that is not redundant, right? In fact, there's not going to be a thing that's not redundant. So I guess this is for all C such that they have no redundant, right? So this is a bad check. That's all useless. Filter. So we're going to take C such that below C, not for all. Below C, all the ones below it are not redundant. Not redundant. And we could do a quick assert. C dot size. I guess it could be 0 because all of them would be not redundant in that case. But C dot size is less than 2. Wait. No, below C dot size should be less than 2. Below C. Okay, if everything below C is not redundant, then for all of those C, if everything below C is not redundant, then below C can't have more than one element, right? Let's just map that. Map below C dot size. Everything below C is not redundant. 0, 1, 2, 3. Everything below C is actually the these are all the ground. Oh, no. These all have either 0, 1, 2, or 3. B2 list this. That's the number there below. Let's have one below. Is candidates a set? So we're gonna look at those. Filter C such that below C dot size is greater than 1. And map to their names, I guess. All those things not be redundant if they're next to something. so let's look at 411. Apparently, everything below it is not redundant. So below blocks 411. There are 2 blocks below 411. And then below that map, are they redundant? False and false. Neither of them are redundant. Okay, there's just an error and I just can't code tonight. There it is. Below B's, map redundant. They are all redundant. Oh, if they're all not redundant, then okay, if they're all not redundant, then sure, there can be more than one. Wait, but they are redundant because they both support C. They both support 411. I got part 1 right. Mhm. Okay, let's get the names of these. And let's look at BS 411 itself. So this is on 42. This is 42 up, right? These two are on 41. 5 to 1, 5. That overlaps. But it's 3 to 5, whatever. And 4, 4 to 2, 4. Oh, oh, oh. X is 5, Y is 1 to 5. That's going to overlap with 3 to 5 and whatever. So these two things both support, and if they both support it, why are they not redundant? There's something with my redundant thing. Wait, let's go back to ANS2. Where did I define my ANS2? This is ANS2. Okay. And now, wait, I wonder how I changed from this to this. When was that? Oh, that is when I stopped making this a set. So that would naturally make the answer higher. What if I did BS? Right? BS at map drops. That's oh, BS is defined below. Sure. Same answer. How are these things below BS not redundant? So there are 2 of them. Let's just check that again. And we're still getting part 1 correct, yeah? ANS 1, 430. Either completely disjoint. The leaves is like pretty straightforward, trivial to implement. And these are the redundant pieces. redundant is a set of bricks. Well, we know that we are counting too high. We also know our redundant count is not exactly correct. Maybe don't partition by redundant, right? Well, if instead of doing all of this, try to do this. Instead of doing all of this, just use dropping. There's no B's. We just do dropping the flat map. Yeah, no B's, no R's. We do this. Da, 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 da. Oh, that is new dropping. Dropping. 558. That a higher answer than what we. That's a lower answer. 60558. Just try that. 60558. Apparently my redundant filter is wrong. My redundant filter, which is necessary for part 1, was apparently wrong. I trusted it to do this. Okay. I'm done. Oh, Blue. Yes, you're asking about. I missed your chat. The diamond stuff yesterday. I did get it. Would you like to see what I did? Are you still here? I'm not sure if you're still here. If you are, I can show you. So, this is my final thing, and we have a breadth first search here. All of this is like assigning variables, and this is my final computation, which I refactored a little bit. It's basically the same thing. The only difference from what you saw last night is this even covering and odd covering. I had the wrong counts of them. So I had assumed that there'd be roughly as many even or as odd coverings. So I just counted like the number of grids, the number of full grids on the inside. I divided them in half, and I split the difference. I gave the +1 to the odd count. Whoops. I gave the +1 to the odd count, but that's not the case. It's actually the number of full grids squared is even is odd, and number of full grids +1 squared is even. And I can show you how I figured that out. So in here somewhere, where is it? Here. You can already see, if you remember this graph here, there's even, all along the diagonal is all evens, right? So it's not like a chessboard because the entire outer edge is even. There's going to be more evens. So looking closer at an example here, right? Oops. So 3 is my number of full grids. If this is even here on the outside, and this is odd here, and as we draw this, then we start to get this like 9 by 9 grid of odd points, or 3 by 3 grid of odd points. 3 being exactly this full grid number, and you have to tilt your head to the side to the diagonal to see the grid, right? But there's 4 by 4 of the red points, the even points. So that's it. That's all I had to fix. There's a tiny little diff because I already had full grids defined, and I just did this and replaced whatever I had before. And I'm happy with my code. This is like less than 50 lines. It's just math. Right? Like I define my points, my midpoints and my corner points there. And then I do my modular arithmetic to calculate the number of grids, full grids, and then there's the steps remaining. This helps me to determine how many steps I need to take from a small corner, a large corner, or the far side. We went over that yesterday. And again, odd covering, even covering, we calculated that. And now for each of our corner points, we step from that point the appropriate number of steps. For each of our large points, do the same thing. And down here, we're like multiplying them by the number of small corners and large corners, respectively. And we do the same for the far corners, and we're golden. So that is that. Let's do a raid. I'm gonna want to check leaderboard results, but I kind of don't. No, I'm gonna check it. Where was I? Sure, still top 3,000, but that felt really slow. A lot of people are gonna beat me to that. And I wonder if I lost. Oh, I didn't lose positions on the Scala Center leaderboard. But still, let's see where I fell for today. Yeah, I was fifth to finish, sixth on the part one. Wasn't my best day. It took me 2 hours to like debug stuff, and I don't know why. But at least we're done. And now we can go raid someone. Twitch, admin the code. What's you still doing admin of code? Oh, wait, Alcazon.
Yeah, I suppose.
I raid them, no question. I feel like they're probably done. But they always have interesting stuff to work on. Okay, it looks like they are done.
And the marked is in the box.
Maybe I'll just do a quick check of anyone else doing. Okay, we've got Bash Cop doing it. That's always sort of fun.
But just thinking about this. If that line breaks like that,
just do advent of code tag.
Take the length of moving.
Zombie Shell is actually still working on it.
This will prevent the double counting. So I don't need any of this.
Okay.
So just return.
Let's do that.
The Gentleman Cat, thanks for the follow. Welcome to the Golang Struggle Bus Pain Town.
Well, thanks everyone for stopping by.
I think I'm close though. So I don't need results.
I hope your family's okay and not getting too much in your hair for this problem.
7, please.
And
0.
Pet Alligator, it's good to have you.
What did I do wrong?
You had to go bed early.
Walk total. Oh, I don't always move. Nice one. Hey, Stu Squared, how's it going? Did you just wrap up? How was your stream? I've been slacking on advent of code. I've been playing video games. I'm undisciplined. I'm not worthy. What the heck is going on? I couldn't code tonight. My code is way too complicated. I think mine is too. But my code is always complicated. I tend to write very verbose code. I pretty much take every instruction in my head and like lay it out. Even though there's like programming paradigms and stuff to like shorten it. I don't know, that's just how I tend to code. So moving is returning 1, 2, 3, 4, 5, 6, 7. Why does it think all of these are moving? What does edges look like? Oh. Wait, that's right. 1, 2, 3, 4, 5, 6, 7. What am I doing? Yes. So -1 would be 6. Total 6. Alright, cool. I do that too. Helps keep things straight in my head. Like my code might be able to take shortcuts, but my brain doesn't. Yeah. I actually think that I find that level of code to usually be did I get yesterday's? I did not get yesterday's. I think I'm gonna like when I run into like a part 2 that takes like more than a couple hours, I probably need to like sleep. Cause yeah. I think when I was younger, maybe I could push through and like